Hello Math 152 students. In this video we'll take a look at a problem and carry it over in 4.1, 4.2, and 4.3. We are going to start on page 184 with problem 28. The context for this problem is we have a researcher wanting to develop a model to predict a bear's weight. So we can't go out and weigh a bear when we see it, but if we could estimate its length using a tool and then use the length to predict the weight, we would be in pretty good shape. So this is exactly what the researcher did. Could we use other things to predict the weight? Maybe, but this might be the most natural or really kind of our best option. So we have 12 bears and 12 rows of paired data. When we're thinking about explanatory and response in part A, think about which one is explaining or predicting the response. So we could think about this as the length explains the weight, or the length is used to predict the weight. So in this case, the length is the explanatory and the weight is the response. In part B, we want to create a scatter diagram, and we want to use StatCrunch to do that and the linear correlation. So let's go back, and you have that StatCrunch icon beside your problem. Let's use our graph option. Let's see. Oh, there we are. Lost it there for a second. Choose your length, and your weight is your X and your Y. We don't have any groupings in this case. For example, if we had tagged each bear as male and female, we could maybe make all the males red, all the females a different color, and be able to identify those by groups, or even create two separate graphs if we wanted to get fancy. Okay, but for right now, let's just hit compute. So it looks like we have a general positive trend. As my bears are growing, or as my bears are getting longer, my weight is going up. Then we could also create our correlation by going into summary stats and then correlation. Keep in mind your book shows you how to do R values or correlation coefficients by hand. We're not going to do that. You can tell by just looking over the examples in the book that those are very time-consuming computations. In fact, most of the time, unless there's just several data points, it's not really worth your time to go through those in practicality. So go ahead and select both of your columns and compute. So I'm going to have us round to 3 decimal places through this entire problem. So pay attention to your rounding on MyMathLab. That tends to be a pretty frequent problem spot in chapters really 3 on, but 4 particularly, because if you don't round appropriately in the beginning, sometimes that carries through with some different errors. So we'll say our correlation coefficient is 0.704. Then our book also asks us to assess if a linear relationship exists. And what they're really wanting you to do is compare the correlation coefficient to the critical value table. They don't reference that here, but in your textbook they say for fewer than 30 data points, you need to decide if that R value is strong enough. So the concept is the more data I have, the more acceptable it would be to kind of just look at the picture and determine if a relationship exists. But the fewer data points, the stronger I want my R value to be, the closer to 1 or -1. Or we could say the closer the absolute value is to 1. Now, in your book, you can access those critical values by going to Appendix A. I would recommend just opening up a new tab, and if you scroll down past the chapters, click on Appendix A, and then it's Table 2. I would just print this out to have handy. And we're looking at an N value of 12. what this value is telling us, is 0.576, is that as long as my r is greater than that, or less than negative 0.576 if it were negative, I'm good to go. So that 0.704 definitely exceeds this value, and we can say a linear relationship does exist. So notice what happens. If you have a small value of n, you have to have a really strong r. As your value of n increases, this approximately 0.4, these are much, much weaker, or your scatter plot is going to be much more scattered and not tightly linear. So that answers our questions for 4.1, and we want to carry over this context to 4.2. Let's go to page 199, and they ask a series of different questions. In this case, they're going to be asking us for the least squares regression line and then some interpretations. So for the regression line, let's go back to StatCrunch. I'm going to leave this and choose regression and simple linear. Selecting my x and my y, you're going to ignore this part with hypothesis testing and confidence intervals. We really don't need anything else. I do want to leave that fitted line plot selected, but right now I'm not going to save anything else. It gives you the option to create predicted values and residuals. But in this case, sometimes we can run into some issues with rounding on your online homework. So sometimes this is not as helpful just due to the rounding issues. So I'm going to pull this over here. And they give us the linear regression as an equation, but instead of putting it into y equals mx plus b form, they put it into b plus mx. Now, they've used the words instead of the x and the y, but if you scroll over to the next page, they give you the fitted line plot, the equation, or the equation plotted, and if you hover over it, it writes it for you, and you can tell it's in the b plus mx, just reversed. So a lot of times we think in terms of mx plus b, and we might naturally reverse the order and write 0.16 or 1694x minus 142.471. So in this case, if I were to round to 2 decimal places and then calculate all of my predictions and residuals from there, I'm going to run into some compounded error versus if I were to round to 3 decimal places, or in some cases even 4. So pay close attention to what MyMathLab is asking you. In this case, they don't specify, and we'll just use 3. Now, the next part was to interpret those values. So we want to focus on interpreting both the slope and the y-intercept. And in our case, let's see. Let's do slope first. And notice they also indicate if appropriate. Sometimes we'll get an explanation that doesn't make any sense, and we could say that. This would mean blank, but it's not an appropriate explanation. So you always want to try to interpret, but whether or not it makes sense is kind of a secondary part. So let's start with that slope. The slope is given to us in StatCrunch as a single number, but when we're interpreting the slope, we want to think about it as a rate of change, comparing the change in y to the change in x. Think about slope as always rise over run. If we want to create something that looks like rise over run, the easiest thing to do is to think about this as a fraction. Think about this as 1.694 divided by 1. I like to write it as the vertical fraction. That's a little trickier to do just sometimes with the formatting. So think about this as 1.694 over 1. The top number tells you the change in y. Okay, so if we think about that, that's telling us how y changes. Then go think about what y is. The y is the weight. So this is telling us something in relationship to the weight, and this one is telling us something in relationship to my x values. Let's make this green. Oh, nope, that's not what I wanted. Something in relationship to my length. I think it's easier to start with the length or the x value because that's always going to be 1. So this 1 is talking about a change or an increase in 1. And 1 what? The x values were our lengths, and go back to your problem and verify that you understand the units. So this length is representing a change of 1 centimeter. Okay. And my top number, the change in my y, this is representing a change in, going back to my context, kilograms. Let's see, what do we round to? 1.694? If you leave your units off, you lose points. So think about these two things, pairing them. I like to start mine using the explanatory in my sentence and then referencing my response. So what this is really telling us is for every change in 1 centimeter in length, my weight changes by 1.694. Now think about changing. This is positive. So if you don't have any negatives, I even sometimes just do this. So that I can say increase. If my length increases by a centimeter, my weight increases by 1.694 kilograms. Now if we had a negative slope, my negative would only go with this one. Right? So be careful here. Think about your change. The 1 is always going to be positive. Pair your negative with the change in 1. So put it together. Sometimes it takes a couple of times to write this out and tweak it to something you're happy with. So I'm going to say something like, for every 1 centimeter increase in the length of a bear, we expect the weight to increase by 1.694 kilograms on average. So your interpretation should reference your explanatory, your response, and use units. Then let's go on to our y-intercept. Our y-intercept we often state as a number, but the y-intercept is actually a coordinate. The y-intercept is a y value that corresponds to an x value of 0. So you can think about your y-intercept as always being 0 and then the y value. So the x value is always 0 for this y. That's the definition of your y-intercept. So that might have sounded a little technical, but what it's telling you is you can always rewrite your y-intercept as a coordinate, and then you have an x value to interpret. So I'm just going to highlight these again, and then a y value to interpret. And actually, let me be a little more careful here. So here I used my green for my x, and my yellow for my y. So we'll stay consistent there. And you want to think about what each one is telling you. The 0 is representing a length. So think about that as 0 centimeters. And think about your negative 142.471 as kilograms. Now this is giving you a pair of data or a pair of points. So think about this length corresponding to this weight. a bear that's 0 centimeters corresponds to